So we are finally going to today talk about the most modern view or atomic model. Um, so the problem with Bohr's model is that we have actually a huge number of different electron energies that are being given off as these electrons are jumping and falling. And even with just a handful of elements, we see way too many possible energy changes that could happen to explain all of them as just electrons jumping up and down within energy levels. So it must be a little bit more complicated than that. Now, I should point out that it it does actually, when we have an atom with the Bohr model giving off light, they do give off a bigger variety of light than you might expect if these energy levels were all just the same distance apart, the way it looks in this drawing. This other diagram over here actually does show you that the first energy level way down here is way, way lower than the second. So there's a big difference in energy from the first to the second, and then a smaller difference from the second to the third, and the third to the fourth, and so forth. So what that means is an electron falling from 2 down to 1 is a much bigger energy drop and therefore a much bigger energy of light than if you were falling from like 4 down to 3, which is actually a pretty small drop. So you might get infrared light given off as an electron drops from 4 to 3, but ultraviolet light as it falls from 2 down to 1. So there is more than just this simple model shows, but it still does not explain the huge number of different energies given off by electrons as they fall back down to their ground states. So basically, we decided that it must be more complicated than that. And one of the first contributors to this idea was Werner Heisenberg. So the Heisenberg uncertainty principle says, let's not think of electrons as like the Earth orbiting the sun or other planets orbiting the sun. Um, they're tiny and they're unpredictable and they're moving super fast. And we've already talked about the fact that they have these wave-like properties. So it's much better to think about the probability of finding electrons. And he said the more we know about the position of an electron, the less we know about its momentum, which is kind of just another way of saying that for something as small as an electron, you can't know both at the same time. Really big particles, like the ones that we can see with our eyes, like a baseball, you can know its position and momentum to almost 100% certainty, both at the same time. But the smaller an object gets, the more difficult it is to know both simultaneously. And so what it creates is you want to think of, rather than an electron orbit where it just simply circles around and around and around, if you were to take a picture of an electron within, like, let's say, a hydrogen atom, which only has one electron, and then take another one and another one and another one, right? Of course, you couldn't do that because, you know, cameras can't pick up something as small as an electron. But if you could, and you lay those pictures on top of each other, after, a couple hundred pictures, you start to get this sort of cloudy picture of all of the places that that electron has been every time you snapped the picture. You can also think of it as just like a probability of finding an electron in a given space. And this picture over here is just another way of depicting the very same thing. And over here in this graph, what we see is probability on the y-axis and radius on the x-axis. And so for that hydrogen atom, its its one and only electron is most likely to be found at this distance, which is about 0.05 nanometers from the nucleus. Um, so its probability spikes at that radius. But notice it doesn't really go to zero on either side. And so what that means is that electron is not necessarily, it's not constantly orbiting at that distance out from the nucleus. It's just where we're most likely to find the electron. So electrons exist not only within energy levels, like Bohr said, he wasn't wrong, but there's also an added level of complexity, which we kind of looked at with the POGLE that we did. So they also exist within sublevels in those energy levels. So just like a building might have floors, but also on those floors it has rooms, sort of just subdivisions of a larger division. And we can think of those sublevels or orbitals as regions where an electron is simply most likely to be found. Some people call them containers of highest probability of finding an electron. So we already know a little bit about at least the names of a couple of these shapes, but we have four different shapes. S and P, which you were a little familiar with from the POGIL, are the first two. And first of all, understand, again, these are not the paths that electrons are taking. If you have a spherical sublevel, the S sublevel, this does not mean that an electron is orbiting in a circular fashion. It just means that this is the cloudy sort of region where we're most likely to find an electron if it's in an s orbital. The same thing for P. P is just twice as complex. It's got these two lobes for each orbital, and it has three different orbitals. And so we can kind of take the number of, well, we can very much take the number of electrons that each of these can hold by simply multiplying each orbital that it can have by 2. Because 2 electrons, if you remember again from the POGIL, I kind of represented it as an up arrow and a down arrow, 2 electrons can fit in each one of these orbitals. Now in an s orbital, you can only have one s orbital per energy level, so like one sunny room per floor. And so for that reason, we can say that we can only have 2 electrons per energy level in this spherical s orbital. Now the p orbital has actually 3 orbitals per energy level, and you can see them there. We have one going vertically, one coming out at you, and one along the horizontal axis. So that would mean each of those holding 2 electrons would give you 6 total, right? Now it's a little hard to picture this, but I found another picture. This is showing the 3p orbitals a little bit elongated, but it's still the same thing. And this final picture is showing how they all kind of fit together. So I just wanted to show you that because I just wanted you to understand that the nucleus would be located right in the middle here, and your 3 different orientations of your p orbitals would be, surrounding that nucleus. So you'd have one going vertically, one horizontally, and one kind of coming out at you, right? But that gives you 6 total that you can have in p orbitals per energy level. Okay. The other 2 shapes, D and F, are really complicated looking. The main thing I want you to take away is that is the number of different orbitals you can have per energy level. So for D, you can have 5. If you kind of look there, you can see there are 5 D orbitals drawn there. Yes, this last one's a little bit funky. All of these are essentially just the result of what are called a wave equation, where you're putting in the various components of the energy of electrons into a calculation, and the computer will spit out for you essentially a 3-dimensional probability of finding that electron. And that's what these pictures are representing. Again, they're not orbitals, or I'm sorry, they're not orbits for the electrons, they're just where we're most likely to find them. So don't get too hung up on the fact that they look so complex. It's just an orbital, and it's more complex looking than the previous 2, but it still only holds 2 electrons. So if you can have 5 of them in this D sublevel shape per energy level, then each of them can hold 2 electrons. That would be 10 per energy level, right? And then the F, even more complicated still, but there are 7 of them, so there you would get 14 per energy level. Okay, so let's take a look at this code, this electron configuration code. The first thing to know is the job of the electron configuration is it tells us the locations or energies of electrons in an atom. It's like a map for where that electron is and how much energy it has. So for aluminum has 13 electrons. So would you get that from its atomic number in the periodic table? So you can kind of match that up. If we look at the periodic table, you see aluminum is number 13, right? And then if we look at the superscripts, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. So the electrons are represented there as a superscripts, and we learned that already in the POGIL. So it has 13 total electrons. It actually has three different energy levels. So those are the big numbers out in front. We have the first energy level represented. We have a couple of second energy level sublevels and a couple of third energy level sublevels. Excuse me. And it has two different shapes because it has a couple of different S's. You know, it has 1s, 2s, and 3s, and it has a couple of p's, but it doesn't have any d's and it doesn't have any f's. So there's only two different shapes represented there. All right, and then you could say how many does it have in its highest occupied energy level? Well, energy level 3 is the highest one I see, and it only has 3 electrons in that energy level. It has 2 in the 3s, and it has 1 in the 3p. And it only has 1 electron in its very highest occupied sublevel, because its highest occupied sublevel would be 3p, and it only has 1 there. Okay, let's take a look at how to write an electron configuration. There's a couple different tools I'll give you. The best one that I'll give you, we'll go over in class, and that's the periodic table. But I also want to show you a couple of diagrams that you might come across if you're kind of looking this up, but it also helps you to understand. Let's take a look at calcium. Calcium on the periodic table sits over here. It's atomic number 20. So it has 20 protons and 20 electrons if it's not an ion. So if we look at this little diagram on the left, this is just showing us like the order of filling of electrons. So each of these boxes represents an orbital, so it can hold 2 electrons. And you always want to fill from the bottom up. We want to fill from the lowest energy up. And so if you look here, our first 2 electrons, of course, would go into the 1s, right? So we're going to start with 1s2. Remember, we're trying to get to 20 for calcium. The next lowest would be 2s, and it can also hold 2. So we have 2s2. And then slightly above that, we have 2p, but it can hold 6 because it has 3 orbitals, right? And so now we're up to 10 total, 2 plus 2 plus 6. And then from there, we would go to 3s, which can also hold 2, just like any s orbital or any s sublevel, because it's only 1 orbital. And then from there, the next lowest would be 3p. And again, all p can hold 6 because they have 3 orbitals. And then you might be tempted to go over here to 3d, but actually the next lowest sublevel is not 3d, it's 4s. And we'll talk about that more in class, but essentially we're just kind of following the order here. So 4s does come before 3d. And if I have this counted right, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. So we are done. That's the electron configuration for calcium. Another way you could see this done is using something called the diagonal rule. I used to use this quite a bit more, but because it's pretty easy to do, you can write this yourself. Just take a piece of lined paper and draw 1s followed by 2s, 3s, all the way down to 7s, and then go down a line and draw your 2p, 3p, and draw all of your p's, and then down another line, and then your d's, and another line, and then your f's. And then if you draw from the upper right to the lower left, a diagonal line starting with the 1s, and then the 2s, and then so forth, this will actually give you the order of filling as well. So starting at the tail of the first arrow, you just keep going, and every time you go through a sublevel, you just insert that many electrons. So for example, 1s can hold 2 electrons, so I would write 1s2. And then I come to the tip of that arrow, so then I go to the tail of the next arrow, and I come to 2s, and again, it's 2s2, right? That matches what we did earlier. And then we just keep going. Now the next thing we come to is 2p, so that would be 2p6, right? And then 3s2, and then 3p6, and then 4s2, and we would be done. So that's another tool, might help you. You're welcome to use, and I'll also show you how to use the periodic table, because that is a tool that we will always have with us. But we'll do that next time.